Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, welcome everyone, and thank you for joining us today. I'm Xie Jiang from Max Planck Institute for Biochemistry, and today it's my pleasure to welcome you to AI for Good webinar series. And I'm very pleased to introduce our speaker today, Mohammad Hakam Shams-Eddin, and he is a PhD candidate in the computer vision group at the University of Bonn and a member of the Llama Institute of Machine Learning and Artificial Intelligence. And his background is in geomatics engineering, and his research focuses on developing deep learning methods for forecasting and early warning systems using remote sensing and climate data. And now, Hakam, the floor is yours, and we are looking forward to your talk.
Thank you for the nice introduction. Let me share my screen. Can you see my screen?
Yes.
Okay. So thanks again. Okay, so today I'm going to talk about AI for early warnings, addressing floods and drought. So we will cover 3 topics. In the beginning, I will talk about flood forecasting, and this would be the longest part. Then we will talk about drought forecasting using AI. And in the end, shortly, we will talk about identifying drivers of extreme agricultural drought, for example. So actually, flood forecasting is closely aligned with the Sustainable Development Goal 13, because extreme floods is expected to rise due to climate change and socioeconomic development. And with the climate change, we would expect that the frequency and pattern of extreme floods will change in the future. And if we could forecast floods, especially the extreme one, earlier in time and with high accuracy, we can mitigate climate change and its impacts. But flood forecasting is also related to the second goal of SGDs, and that's it. If we can forecast floods, the extreme ones with a high accuracy and early in time, we could make human settlements more safe, resilient, and sustainable. And if you look at floods, so it's one of the most destructive natural disasters in the world. And whether you are here in Europe, America, Africa, or China, so all people are affected by this. So this is a global issue and causes a lot of damage and fatalities. So here is an example from the R flood here in Germany. It happened like 4 years ago and caused a lot of damage and fatalities. And you can see from the photos how extreme this flood was. So flood can be categorized into different types. And in our work today, we will focus on one type of flood. It's called riverian flood or fluvial flood. And this is highly related to river discharge. And by river discharge, we mean like the amount of water that flows in the river. And this is highly proportional to the height of the water. So the more discharge you have, so you could have higher water. So, and the flood could happen like when the flows arises and then the water goes to the nearest land and cross the banks of the river. So we will focus on this key variable to determine floods. And to make it like more clear, so river discharge looks like this. And in the y-axis, you have the flows, like cubic meter per second. And then in the x-axis, you have the time. This is, for example, station here in Cologne at the Rhine River in Germany. And if you look at the time series, so in the dark part, you have like the flow-fast reanalysis. You can think of it as a simulated river discharge. And in the dark cyan is like the observed river discharge. But overall, if you look at the time series, you can see how complex it is like to do the prediction. So somewhere on the Earth, you could have some annual cycles for the river discharge. But in general, it looks like this, and it's very hard to do the forecasts. And usually we define flood based on thresholding. So the dashed line you see, this is called like threshold defined by return period. So for example, a return period of 2 years means like, okay, there is a probability of flood to happen at this threshold 50% within 1 year. And if the river discharge across this value, we consider it as a flood with 2 years return period. So this is typically how we define the flood. But it's actually not so easy to do this, because if you look at the water cycle, like here, so river discharge is highly dependent, for example, on meteorology. For example, if you have precipitation, so rainfall, and if you have like land cover, vegetation land cover, how will the rain affect the river? Will it be observed, reflected to the atmosphere, etc.? And if you have like snow and you have some annual cycle, how the snow will melt and affect the river itself. And of course, if you want to do like a long-term forecasting of river discharge, then you have to account also for the groundwater storage, etc. And of course, if you have human intervention, like it's become even more complicated. But fortunately, we have actually hydrological models that can simulate river discharge, whether this is like physics-based model or AI model. And this is like a typical way how we do the warning. So you have hydrological model that output river discharge, and then you have inundation models that model the extent and the height of the water, where we have like flood hazards map, and then the warning can be issued. So today I will focus only on the hydrological model. So on the modeling side, just to get the river discharge. This is actually the first step and most important step in flood forecasting. So I'm gonna give 2 examples of the systems that's used for flood forecasting. The first one is called the Global Flood Awareness System, operated by ECMWF. So you can think of it as a physics-based model where it used, for example, meteorological forcing or weather forecast, combine it with land surface model to get the surface subsurface runoff and give it to a hydrological model list flood. And also incorporate some initial condition from ERA 5 and static river attribute to output ensemble river discharge. So in summary, it like combine numerical weather prediction with hydrological model to output the ensemble river discharge. And if you look at this flood hydrological model, so it's more like conceptual model. So it's based on simplified physics concepts to compute the river discharge and the routing. So the system also looks like this, the operational system operated by ECMWF. So on the left part, you have the initial condition from ERA 5 and GLOFAS, and then the system uses ECMWF ensemble forecast to forecast how the river discharge would look like into the future. But the problem is like such a model is very expensive to run. And here's why AI comes to the play. So Google also has its initiative flood forecasting. So it's had they developed their own operational system for flood forecasting, and they use an AI model based on LSTM. So an LSTM is just like a type of a neural network that's used to do the temporal modeling. And it has been shown that like AI model like LSTM can outperform the physics and conceptual model in hydrology. It can also forecast higher accuracy river discharge, also on a global scale. So we call also such a model is like a regional model, because you can use one model, unified model, at all stations or the point without needing to calibrate at each station separately. So it's called regional model. But if you look at it from an AI point of view, so this is like a local model, because the LSTM model, if it wants to forecast river discharge at one location, it won't be aware about the conditioning in the neighborhood. So it will only take the input data from one location and try to do the forecast at this location without looking at the neighborhood. And here actually we ask the question, okay, can we build an AI model that improves flood forecasting and provides high resolution prediction globally? And this was actually the motivation behind our model, which is called RiverMamba. So the motivation is like this. So, okay, we want to have initial condition X at time T, and we want to forecast a medium range river discharge up to seven days into the future. But we want actually to consider two things. So the first thing, we want to have an AI model that's vision-based model. So this means if you have a point in the middle in the river, and we want to do the prediction there, we want the AI model to be aware about the conditioning along the river. So if there is a flood in the upstream, we want also the model to be aware of this. And actually, we also want the model to be aware about the conditioning in the neighborhood. So if there is like some clouds, precipitation coming, we want the model also to be aware of it. So the second thing, we want to build the model that's consider uncertainty in the meteorological forcing or weather forecast. So if you think of it, so river discharge is highly dependent on how we forecast the weather. So for example, temperature, precipitation, wind, etc. And here in the bottom right, so let's say you forecast precipitation to be like this, but in reality, you would end up with like some slightly deviation from the reality, right? So we want the model to be aware about this uncertainty in the weather forecast. So maybe you forecast that the rain will fall in this spacing, but maybe it will fall in multiple ones. And we argue these things are important to build a hydrological model. Okay, before I show the model, so just we look at the data. So for this work, we use, so the river discharge looks like this. So we have, so we remove point on ocean and sea, of course, because we don't need river discharge there. We also remove point where we have very low flow or desert, so we don't need this. And we end up with 1.6 million point at 0.05 degrees, so about 5 kilometers. But of course, so this is for experiments, but in the end, we can generate the full resolution, which is 3000 by 7200 pixels. And if you look at the data, so this is not actually an image, it's like sparse input, and it needs some spatial modeling. So RiverMamba looks like this. I won't go into details, but I'm just gonna give an overview about the model. So it's not just like becomes like a black box, just to get an idea how the model operates. So in the beginning, we have initial condition. So we use here CPC data, which is like precipitation product. We also use error 5 reanalysis and GLOFASS reanalysis. And we shift this input in time to mimic like some operational setting. Then we use the embedding. So this is like just an AI to prepare the initial condition to be input to the model. And then we have the hintcast layers, where each layer has its own hintcast blocks. And each block has like serialization. This is the way how we actually connect the point with each other. I'll explain this later. And then we have the Mamba block, which is the core of our model. And then we have some multi-layer perceptron, which just like to add some nonlinearity to the model. We have also skip connections, it's just technique in deep learning to stabilize the training and extract features in a better way. And we also add like static river attributes. So if you think about, or even if you heard about it here in AI for Good, so if you have like similar weather condition, this could lead to a different impacts depending on the landscape. So maybe if you have the same like meteorological forcing but different landscape, you would end up with extreme floods or normal floods. So it makes sense to access information to the model. So we use this technique called location-aware adaptive normalizations. It's just a way how to incorporate static information to the model to be aware about the landscape. So now I'll explain the serializations. The serializations is just the way how we add spatial connections into the model. So for this, we use space filling curves. And space filling curves, you can think of it as like, if you have a discrete space, you can use space filling curves to fill in the space and connect all the points within one sequence. So the Mamba module inside RiverMamba is actually designed originally for natural language problems and to operate on a sequence of words. But in our case, it will operate on a sequence of points. So let's look at an example. So here in the top, so there are many types of these curves, and let's look at, like, for example, Hilbert. So we define the curve, and on the far right, we have a simplified version of the sphere. And in the middle, we have the zoomed in version over the Earth. For example, if you sample some points and you want to connect them, they will look like this. Now I will explain like the Mamba module inside the model. So I won't go into details, but just to give an overview. So Mamba is based on state space model, which transfers the current state X into state Y based on a hidden state H. And to use this for AI and deep learning, so Albert Q and TreeDAO like discretize the system and make it time variant, so we can use it for training AI models. So again, here's zoom in version in the block. So again, the details are not important, maybe what's important is that. So this state space model is actually a recursive like system, but we don't do it like this. We run it in parallel on GPU, so it becomes much more efficient. And we actually run it 2 times, one forward and one backward. So to make it maybe more clear, so let's look at an example. So here we have an input point, which looks like our domain, and we give it to the AI model. So in the beginning, we run a forward pass. So this is the first block of the model. We define space filling curves, for example, like sweep curve looks like this. And we do the scanning until we reach this point in the middle. And this point, when the model will do the prediction for it, it will be aware about the condition that happened along all these points before that had been scanned. Then we continue the scanning and we go then backward in the scanning. And when we reach the same point, this point will be aware about the condition in the rest of the domain that didn't see in the forward pass. So like this, each point will be aware about the condition in the full domain. And we combine them together and then go to the next step, which is the next block. And if we add different like scanning strategy for each block, then the AI model will like collect spatial features for each point from different spatial perspectives. And the more deeper you go into the model, so the model will get like more complex information. And this is just an overview. So if you compare like the RiverMamba, the core module Mamba with like traditional transformer, which is like an AI module based on flash attention, for example. And if you have like far on the right, like 1.5 million points, and then you have also 4 days hintcast, so you end up with 6 million points, and you connect all of them together, you actually, the AI model can do it in 4 seconds. Compared to a transformer with an efficient implementation, it would need like 8 minutes. It's just to get an overview about how efficient this system is. Okay, so this was about encoding information from the initial condition. And then actually to do the medium range forecast, here we incorporate the HRES, which is the high resolution meteorological forcing from ECMWF. And we use forecasting block. So the way how we structure this is similar to the encoder that we showed before, but additionally we incorporate here the weather forecast from ECMWF. So we just add it, we use embedding and use the same setup as before, as I showed before. And then, for example, for 1 day lead time, we get also delta X, which is like just the difference between the river discharge with respect to the initial condition. And we don't use rollout, so we don't do recursion, which we just, we do the forecast for up to 7 days in one run for the model. And we connect all this together so the model can also account for uncertainty in the temporal dimension as well. So this was just like an overview. We also trained the model with RMSE loss, and we waited also for the flood events. So if we have very extreme events, give it more weight. So this was just an overview. So now for evaluation. So yes, we generate like full maps, but for evaluation, we evaluate the model where we also have observational data. So here we use the GRDC observation, where we have like about 3,400. And this is not the results, this is just how the reanalysis from GLOFAS agrees with the observed river discharge. And as you can see, and here we will evaluate the model on these stations. And you can see that like overall, like the simulated and observed river discharge agrees well. So this is just an example about the results. So here we train the model to predict simulated river discharge from GLOFAS reanalysis up to 2018. And then we do validation from 2019 to 2020. And we test the model from 2021 to 2024. And the top, you can see like the F1 score for the flood forecasting. So F1 score just combine recall precision. It gives us an idea how accurate the forecast is for the 2 years return period. So here is shown a box plot where each point represents one station, and in the middle line is actually the median value. So here we have also like the results for 24 hours up to 168 hours, so as 7 days in the future. And here we compare to LSTM model as a baseline. So this is similar to the structure of the Google's model, but trained in our setting. We also compare it into persistence baseline. So this persistence baseline just take the last observed river discharge value and make it consistent for the 7 days. And as you can see, like RiverMamba improves the results with longer lead time. So here we can also see the results from different perspectives. So on the left part, we can see the average F1 score over lead time per return period. And on the right part, we can see the average F1 score per lead time. So here we can also evaluate the model spatially. So we see where the model fails and improves the results. So here's the results for 5 years return periods flood events at the 7 days lead time. And this is just comparison like RiverMamba to a local model like LSTM. And we can see that like RiverMamba improves the results on 90% of the stations. So we can also look at the confusion matrix. So this is the results for 4 days lead time. On the left part is the results for RiverMamba. On the right is for LSTM. So in confusion matrix, we have on the y-axis, we have the target or ground truth, so the real value. And then in the x-axis, we have the prediction for different classes. So starting from normals, mean no flood, up to 500 years flood events. And for example, if you look at 1.5 year return period, so if you look at the left part, so this was 53% predicted correctly, and 30% predicted as non-flood, and 16% predicted as 2 years flood. And if you compare LSTM to RiverMamba, you can see that like on the left, you have a better prediction of the extreme floods. Okay, now we move to observation, where we also evaluate the model on the observed river discharge GRDC data. So here's the results for 2 years return period. Here we also include the Global Flood Awareness System from ECMWF. Yeah, and you can see like, of course, here the results is not as good as on the analysis because you have like a human intervention and it's very hard to really forecast the observed river discharge. But overall, in general, like RiverMamba still outperform all baselines on the observed GRDC. So here we move, so the results I showed was on engaged setting. So we train the model up to 2018 and then we test it forward. But here we do an evaluation on engaged setting. So here we compare to Google Reforecast, the published version. So we don't train LSTM, we just take the published Reforecast from Google. And in uncaged setting means that, okay, we don't train on all stations. We take some station out and we train the model, and then we test on this station that the model didn't see, and we can get an idea how the model generalized in the spatial domain. So on the left part, we can see the average F1 score per return period, and on the right part, we can see the average F1 score per lead time. As you can see, like RiverMamba still works in an uncaged setting. So here is just an example on the hydrograph. So this is 1 day lead time, a model trained on reanalysis for an extreme flood events that happened at Sauer River in 21 in Germany, July. As you can see, like almost all baselines like works good actually. And you can see that RiverMamba captured the extreme flood very well. Okay, here I show some qualitative results. So here is an example from China in June. So on the top part, we have the close reanalysis as ground truth, and in the bottom, we can see the prediction by RiverMamba. So from the left is 1 day lead time, up to the right, 5 days lead time. And of course, the spot you see doesn't mean like you have flood here, but here where we expect to have a higher river discharge. So here's another example from Central Europe. So here we had very extreme flood events that happened from storm and heavy rainfall in September that affects many countries in Central Europe. And as you can see, like the model captured the events very well. It was also followed by another events in the beginning of October, which affects southeast of Europe. And as you can see, like the model captured this, it was also followed by another events in Australia. So here is an example from the Spanish flood last year, a very extreme flood. So as you can see, the model captured this up 3-4 days lead time. So this was in October, and it was followed by another event in the end of October. Here we actually have data just until the 30th of October, I think. Yeah, but as you can see, like, okay, the model captured the events to some extent up to 4 days lead time, I'd say, or 5 days. Of course, the localization is very hard still. So one needs inundation models. Also, one needs to improve the results more. But in general, I would say it works. So here's an example from in Germany. For example, this is a Saarland flood captured 4 days before, and also 1 day lead time. So this was, okay, this is an example of false negative. And then, okay, this was in Augsburg in the south of Germany, where we had also an extreme flood in the end of May, beginning of June. And this just gives an idea how the model like works. Okay, and then there was an event in Australia. It was captured by Okay, this is the last example I want to show. So this is from USA, different environment, different continent. And we can also get an idea how the model performs, for example, in US. So this in February, there was like extreme also flood caused by atmospheric rivers. So here, of course, on the right part, we have a lot of desert, no flow, but just to get an idea how the model operates. So with this, I will end the talk about flood and talk a little bit about agricultural drought forecasting. So here I will talk about a model called Focal-TSMP that can forecast extreme drought. So extreme drought forecasting is also related to the second goal of SGDs, and that's it. If we can forecast extreme drought with high accuracy and early on time, we can improve nutrition and promote sustainable agriculture. So just to get an idea about how we define drought, so we define it based on remote sensing, satellite measurement. So here the satellite measures some reflectance on the ground. So here we look at normalized difference vegetation index, or NDVI, which is proxy of moisture, and it's a combination of near infrared and infrared channel. And you can think of it like, okay, if you have like a healthy vegetation, green one, you will have a higher NDVI. And if it's like unhealthy, dying vegetation, you will have a low value of NDVI. We also look at brightness temperature, which is proxy for the thermal condition. And you can think of it like, okay, if you have like a heat wave or something, this won't be so good for the vegetation. So we also want to look at this. And the way how we define droughts, actually, we have this NDVI and brightness temperature, and we look at the long-term climatology. We can define indices like vegetation condition index, thermal condition index. We combine them together, and then we get like a vegetation health index, which is related to agricultural drought. And this index goes from 0 to 100. So the higher, the better. The low is like not so optimal condition for the vegetation. And the idea is actually in Focal-TSMP, if we want to do long-term agricultural drought forecasting, it's very hard to do with AI. So if you want your AI model to forecast 2 years into the future, maybe if we combine it with climate simulation, it will be easier to do the forecast. So here the idea is that we have remote sensing products up to now and in the past. We can take climate simulation and train an AI model to predict this remote sensing data from the climate simulation, which will serve us as a control panel. And then in the future, we take the same AI model that we trained before, and then we can have different scenarios, different climate scenarios, and the AI model can tell us how the agricultural drought will look like according to these simulations. So the simulation we use, it's called TSMP simulation. You can think of it as 3D modeling of the Earth. Of course, we have time, so it's going to be 4D. It's a regional climate simulation, so over Europe. And the simulation consists of 3 main components. So the first one is called bar flow, which is like for hydrology, it simulates the dynamic processes of the water in surface, subsurface. And then we have the CLM model, which is land surface model. And then we have the Cosmo model, which is like old version of numerical weather prediction model. And all of these components are coupled together and connected so they can interact with each other. And this will be actually our inputs to the AI model. So the simulation also includes, like, just to get an idea, so the simulation includes like simulated humidity, total cloud fraction, radiation, the height of the cloud, and the wind speed, something like this. So this is what we get from the climate simulation. And the AI model looks like this. So I won't go into details, but just to get an overview how this works. So on the left part, we have the climate simulation from TSMP. And then we have an encoder-decoder structure. So the first, the AI model encodes this climate simulation. And then with the decoder, the model tries to map this TSMP simulation into remote sensing products like NDVI and brightness temperature. And then with climatology, we can get this predicted NDVI and brightness temperature and have the vegetation indices. So just to get an idea how the model works, so we use here focal modulation for the model. So on the right part, if you use something typical like transformer, self-attention, and you want to do prediction at this query point in red, so usually what we do, we go to this location and then we get the neighborhood and we measure similarity with the neighborhood, collect features, and able to do the prediction. But this is actually like computationally expensive. So we use in our model the focal modulation module. So it's shown on the left part. And for this, if you want to do like prediction of NDVI, for example, on the red query, so we start from local to global. And this is how the model operates. So it starts from local neighborhood to global neighborhood to collect some feature information in order to do prediction. But this is just like an overview how the model operates. So the results looks like this. So on the left part, we can see the predicted NDVI, and on the right part, we can see the predicted brightness temperature. And of course, with climatology, we can get then vegetation condition index on the left and thermal condition index on the right. And if you combine them together, we get this vegetation health index, which is like related to agricultural drought. So we can also see how the model performs. So here we trained the model up to 2016, I think, and then we tested 2017, 2019. On the left part, we can see the observed VHI from remote sensing, and on the right part, we can see the prediction by Focal-TSMP, which is a combination of AI and a climate simulation. And of course, we don't expect these two to be overlap 100%, but we can get an idea where the simulation works, where the model works, and we can get like a rough estimation where we would expect extreme drought in the future. And this actually vegetation health index can be classified into different classes. So we define some thresholding, and for example, we say, okay, if VHI is less than 20, then this is extreme drought. And here is shown, like, for example, in the yellow, we have like a moderate condition up to like extreme agricultural drought in red. We can also compare the model performance with some recorded database. So here's an example of the prediction in summer 2018 in Europe, where we had like heat waves and drought events that was recorded. But how good can the model generalize to different scenarios, actually? So we asked this question, and we trained the model with a control run, so the same, similar to the one I showed before, to see how the model performs, and okay, we pre-train it, and then now we run different scenarios. So here we run a scenario where we change the land use land cover in Europe. So on the left part, you can see the predicted NTVI from the control run, the one as before. And in the middle, you can see the difference for NDVI between the control run and the climate scenario. So here we do a change of the cropland and the grassland in Europe. So, and if you want to look at the changes, so on the left part, we can see what happened in the scenario. So what was the differences between the control run and the climate simulation? And on the right part, we can see which changes happened into the NDVI according to the model. But this is actually not the end of the story, because okay, let's assume you have an impact of extreme events like agricultural drought. In a follow-up work, like we ask the question, okay, but which climate variables are associated with this impact? So we try to identify spatio-temporal drivers of these impacts of extreme events on the vegetation. And this looks like this. So on the right part, you have some impacts of extremes, which is agricultural drought. We get here vegetation index as proxy. And in the middle, you have like atmospheric and land state variables. And we consider drivers for the impacts of extremes as anomalies in these variables. So we consider anomalies in the temperature, soil moisture, evaporation as drivers for the impacts of extremes. But the task is actually very hard, because like these impacts of extremes can happen at different time and location than where the drivers happen or where the anomalies happen before. So here also we can use AI actually to try to identify these drivers and localize them in space and time. So the model looks like this. Again, I won't go into details, but just to give an overview. So on the left part, we have like an input reanalysis data on a weekly basis. We have the mean and standard deviation per week. So for example, we have soil moisture, 2-meter temperature, and humidity. And then with AI, for each one of these variables, we extract features. And in the next step, we use quantization layer. And you can think of quantization like a function that maps continuous values into discrete ones. So here we have like the extracted features from each of these variables. And with quantization, we can convert them into binary classification. So we can convert them into two things. Either it will be 0, which means this is like a normal condition, for example, for soil moisture. At this time and location, the condition here is normal, and it won't be associated with any impacts into the future. And the second class will be like in red, it will be 1. So this means, okay, the soil moisture here, for example, at this time and location, it will be associated with some impacts into the future. And in the end of the model, we use classifier 3D-CNN, just an AI module that takes these identified drivers and predict the impacts of extremes. Actually, we are not interested in predicting these impacts. We are interested in identifying these drivers. But the high-level idea of the model is that, okay, if we can take these identified drivers as input and give it to the model, and the model can actually predict these impacts of extremes, this means these drivers should be associated with these impacts. So in other words, we make the prediction of the impacts of extremes conditioned on the identified drivers. So the model can only focus on what's important or related to the impacts of extreme from these variables. Okay, and here I'm going to show some results from real-world data. So on the top left, we have some extreme drought as measured from remote sensing at time t0. And then on the top right, we have the prediction by the model. And in the bottom, we can see the identified drivers up to 7 weeks before the events, for example, for evaporation and soil moisture. And if we run it with time, like we can get an idea, okay, according to the AI model, how these drivers and anomalies move in space and time. And for example, and as an extended step, one can focus on specific events, impacts, and then tell the model, okay, where was the driver of this event? It's just to get an idea about the prediction. As an application also for this model, so this is similar to the one before. So on the left, so we have like some reanalysis data from now, and we train the AI model to model the distribution of anomalies, for example, in the land and atmospheric state variables. And then if we have different scenarios and different data, we can take the same pre-trained model and see if we will have like statistically different in the distribution of these anomalies in the atmosphere, for example. Or if we add some human like intervention, anthropogenic drivers, we can see, okay, how these anomalies change in the atmosphere. So, okay, with this, I would end my talk. But before this, I would like to thank my co-authors, actually, Ikwi Chang and Stefan Collet from Jülich Research Center. They are co-author of RiverMamba. And of course, Jürgen Gall, who funded and substantially contributed to all works I showed today. So thanks to them. And of course, thank you for your attention.
Okay, thanks a lot. And it's a very nice talk. And let's open the floor for questions. Yeah, probably I can kick off one question. So I like the first study you showed that you designed some model architecture to capture the spatial dependence along the rivers and how sensitive are the results to the design choice, and what did you learn from experiments with different approaches?
Yeah, so actually what we learned is that, okay, if you can use like a local model like LSTM and without any spatial connectivity, and you can still get a good result. But if you want to use like our model, it's important to add some spatial connectivity because the model is designed to do this. We tried different ways to define the curves and do it separately with ablation study. We noticed that almost whatever pattern you use, the model works, but the best results you can get if you combine all of them, so the model can look better into the neighborhood. So I would say whatever kind of curve you define, the model will be robust. Because the way how this state space model is defined is that any point on the curve can be in theory connected to any point along the curve through the hidden states. And it has like a very huge receptive field. This is what we actually learned from the experiments.
Okay, thank you. And Marcus has a question.
Yeah, thanks also for your very nice talk. I guess my question was very similar. So I was basically asking what basically if you compare the LSTM approach with your approach, what do you think really makes a difference? But what you basically said, what makes a difference is really this connectivity in space. And but you also you had two different ways of connecting, and there are of course probably infinitive possibilities to do the connection. So why did you choose these two, or you obviously wanted to use both at the same time as input, if I see correctly? So why is that, or how did you come to this?
So actually, if you think about it, so adding spatial connectivity to model like river discharge should actually help. So if you have some flooding in the upstream, it should be like very informative for the model to do it in the downstream. So we also add additional experiments in the ablation study where we remove the spatial connectivity completely from the model, and then the performance really went down. But we also get like just like 4 days as input as a hindcast. Maybe if you increase it, maybe more, and maybe the results will be better. But overall, I think the spatial connectivity was the key part to add spatial connectivity. And the second thing is actually the weather forecasts. So if we add spatial connectivity in the hindcast part, where we encode just the information from the initial condition, and remove spatial connectivity where we have weather forecasts from ECNWF, also the performance is not so good because the model then highly depends on the weather forecast in one location and doesn't like really account for uncertainty. So this was another key part. And the third thing was actually the loss function which we use, which is like a weighted loss function that also helps the model to predict extreme floods more accurately.
Sorry, but basically, but you use this Hilbert connection together with the, I don't know this, I don't know how you call it. So you needed both together to get good results, or?
Yeah. So actually, in principle, you don't need both. You can use one because the Mamba module inside the model can actually connect any point on the curve to any point on the curve, whatever the distance between them. This is in theory, of course, because you have like a hidden state and then it can connect it. But you can get also good performance, but the best performance you get when you combine different
Thanks.
I can continue with another question. So when you train your hydrological flood model, so I'm wondering, how do you consider the human activities like dams and the water management?
Yeah, so far this was not taken into the account in the model. It's very hard. So you have to incorporate this into the model. And you can see actually clear difference between the performance on the reanalysis compared to GRTC observation. Because this GRTC observed the discharge is highly affected by these human interventions, the dams, irrigation, and this was not taken into account for the model, at least explicitly. So yes, this is a limitation, but it's like an open question how to incorporate this.
Okay. And because you train your model on the global reanalysis data, so how do you avoid simply your model that just learn the bias of the reanalysis? And how to deal with this risk?
Yeah, so actually for evaluation or reanalysis, yes, we train the model on reanalysis. But when you want to go to an observation, we fine-tune the model on the observation. So we pre-train it on reanalysis. Of course, this will have some biases, and then we fine-tune it on observation, of course. Yeah, so, right.
Okay. Yeah, nice.
So we have no questions from the rest of the audience. Usually they appear in the chat. But maybe I have another one. So I found it also very interesting where you said you were going to detect kind of these droughts that can occur anywhere. So basically, it's not directly, it doesn't need to be directly synchronous with the drivers. And I wonder how you can distinguish, let's say, associations that just happen. If you have some, let's say, some waves, let's say, over the globe, and a kind of causal relationships that are kind of happening.
Yeah, so actually in our work, we didn't address like a causal relation. It was just like correlation and some association. Okay. And I think so what we do, we don't say, okay, this is like causally affected by these drivers that we identify, but maybe with subset of them. And this needs actually an extension of the work to look at the causal effects. So we didn't address this yet in our work. This is just like correlation, association.
Thanks.
And actually, so the one I showed, this was actually like the overall, like you have some spots of impacts of extreme, and you have the spots of the identified drivers in land and atmospheric variables. And an extension would be, okay, I go to some events, I localize it, and I can then tell the AI model, okay, only for these spots, the small one, tell me which drivers are associated with this. So this would be an extension, yeah.
Thanks.
So maybe I have another question about from research to practice. So you show that this deep learning model can forecast the extreme events with a very high resolution. But when we think about moving from a research prototype into the operational early warning service, and things can be get quite complicated. And because you need to consider the lead times, resolution, and the reliability, and it is not always clear where to set the trade-off. So how do you see this transition happening in practice?
Yeah,
If you,
so
so if you deploy your model into, for the real world use.
Yeah, so when we designed the model, we tried to make it as near to the operational as possible. So that's why, okay, we use like some input data and we shift them in time. But if we really want to make RiverMamba operational, so there are many ways we have to consider. So first, we need uncertainty. This is so far didn't implemented into the model. So far we have deterministic model, and we should add some uncertainty. We have also to add some nowcasting. We didn't use this. This will improve the results a lot for the near lead time. And we have also to replace this Era 5 land with its near real-time Era 5. So in principle, it's possible to do it operationally, but one needs some adjustment into the model. But of course, how the model will perform in real time is another story. But in principle, we try to make it as near as possible. And the GLOFAST system I showed, like the physics-based model, is actually operational. And in principle, it can work.
Okay, thanks for sharing the insights. Yeah.
Thanks.
So it seems quiet in the neural network. No questions from the audience. Okay, since no more questions are coming in, maybe we can move towards closing. Yeah. Okay, so I want to thank Hankam for sharing his work again, and thank you all for joining and contributing. And with that, and we'll close here and hand over to the outro video.
Thank you.
Yeah, bye-bye.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.